doing the midterms. So I believe you have already submitted midterm number 1, which is due today. So there's that midterm number 1 where some problems and questions regarding fundamentals of power. And then it also covers something from motors in chapter 2, and then also from fundamentals of lighting in chapter 3. Okay, so that's due today. Then last Monday, we watched the video for single phase transformer. So that's out there. So that's going to be due on Saturday, no, Friday, this Friday. And today we are going to do lab number 2, 3-phase power and transformers. We will watch the videos and then the handout. It's already posted. If you go to the Blackboard, it should be posted already there. Okay. Then the roster is this. Okay, so here are your attendances. Okay, so then today this is going to be number 15. So please write your name on the roster for Mr. Habib will take care of the attendance list. I'm just putting here some attendance to a few of you who are in my screen right now. Okay, but don't worry. Just put your name on the roster in the chat, and we'll get you on the roster. Fine. Okay, so now let's see. Let's go and look at the site. Okay, so then let's look at the assignments. So this is what you can see. There are the 3 midterms there. So midterm number 1 is due today. So that's your first concern. You need to finish that and submit it before midnight. Okay. Then midterm exam number 2, which is the lab described last Monday. That's on Saturday, March 1st. So something is wrong here. Let's see. Saturday is going to be March 6th. So let me quickly check. When is it due? Because there is a mistake there. This one here, midterm number 2. So it's due on Friday. It's due on Friday, okay? So this is not Saturday, this is Friday. All right. So now this is fine. So now let's say, watch midterm number 3. Watch the videos, part 1, part 2, and part 3, 3-phase transformers, and submit the Word document on Monday, March 8th. Yes, Monday. Okay. So then let's watch those videos. And the assignment, okay, the assignment, the document also, let me show you the document. Hold on. Please open the document also before if you start watching the video. Here is the document. It looks like this. Okay. So this is the document we are going to fill after watching the videos. So it talks about the three-phase outlet. So that's the photo of the three-phase cord. So it has 4 wires, black, white, red, and green. These are the little transformers, the schematics. And these are the photos that you will see in the video. So there are 3 transformers, each a single phase transformer. Okay. So then let's get started with the video. These are the loads for the transformers. So let's get started with the video, okay? So hold on. Now I will go to Panopto here. Okay, so these 3 labs, but we start at the bottom. See, part 1 is at the bottom, part 2 in the middle, and part 3 on top. So we start on the bottom. Good day to you again. So this is our three-phase power control. So first, I would like you to see this little yellow unit. So they are the three-phase, single-phase controller. So each of these is a single-phase controller. But then notice, each transformer on the primary has 4 windings, and on the secondary, it also has 4 windings. Each of these has 4 and 4. So therefore, it's a combination of 2 transformers in the same job. So let's see how they look. They look like this. There are 2 transformers on the same yoke, on the same magnetic yoke. Now, the ratings of the transformers are the primary, the secondary.
Hey, sir, we can't hear this video playing.
No?
No, it would probably just be better for us to watch it on our own.
Yeah.
Yeah, the audio's cutting out.
Okay. Then if you watch the 3 videos, the first video is 12 minutes. The second video is 8 minutes. And the third video is 5 minutes. So that's 25 minutes, okay? So please go ahead and watch them. And then we open at the end of them in half an hour, we open a review question. Hello. Almost ready, okay? To continue the class. Can you
Almost.
hear? Can you hear me?
Yes.
Okay, so then let me stop this. So here is the picture of the little transformers on the primary. Connected to 208 volts in a delta connection. And on the secondary, oops, where is the second? No, sorry, I'm not looking at the secondary here. Let me see if I have it here. So I want to share with you now the report that you have to fill for the, this is the report. Can you see the report?
No.
Hold on, I'm sharing the screen with you. Okay. So this report is the one that you need to fill out. So you start in page number 1, your name, the transformer kit, omit, the objectives, the gain familiarity with three-phase power, wiring and terminology, observe voltage and current relations in three-phase transformers with multimeter and oscilloscope, determine three-phase voltage phasors, make delta and Y connections at a transformer's primary, make delta and Y connections at a secondary, and the three-phase load, mount, measure balance and unbalanced currents. Okay, so then the schematic that we are going to see is in page number 7. This is the schematic. Okay. So then you can see that the connection to the primary is in delta. See, this is transformer number 1, transformer number 2, transformer number 3. So in the primary, we have a delta, these single jumpers. Okay, and then the return conductor from the third transformer to the beginning of the first transformer, 2 lanes to this. Okay, on the secondary, the transformer is going to be 8 volt. So then the transformers are connected in parallel in the secondary. And since we need, we specify a star connection, then in the secondary, the neutral right here is connected to A, B, C. Yeah, it's right here. Look, all terminals number 8 of the secondary number 8 are connected to the neutral right here, and then also we have 100 ohm resistors connected to phases ABC and to the neutral. Okay, so this is the connection that we are using. So then let's go back to the equipment. So the oscilloscope, the multimeter, the cord, the breadboard, and the resistors. The outlet for 3-phase, the core for 3-phase. Okay, so in the lab, Okay. So then we start here, B, kit number 2, 100 ohms, 10 watts. So this is the connections that we have, okay? Then section number 2, again, 500 ohms. Okay, then section number 3, multimeter measurements. So putting the multimeter on lines black to green, red to green, and white to green, we get these voltages. So these are the, and then you must complete the average, okay? Don't forget this, you must complete here. So these are the phase voltages. And then these are the line voltages, black to red, red to white, and white to black. So again, you need to complete here, do the averages, and then verify the square root of 3 rule. Divide these voltages and verify that are they equal to a square root of 3, yes or no. So here you put the result. You write the result here. So we must verify the square root of 3 rule, okay? Then the secondary voltage, again, same procedure. So you must write the averages for phase voltages, for line-to-line voltages. And then with the averages, calculate, is that equal to a square root of 3? Yes or no? Okay. Hold on a second, please. Now power, section 4, power. So look, in the video, you see how did we measure 81.8 milliamps. That's a measurement. What's the expected current? So it's going to be the phase to line voltage in the secondary divided by the resistance. Okay, so then you need to put the value here. And then you can calculate the power dissipated in each resistance. Okay, with 81.8. So using the measurement, calculate the power dissipated in each resistance using the measurement, the measured values. And then the total power, so it's going to be 3 times this power. Okay, B. So let me put here a footnote. In B, use measure values. Okay. Then next, again, we measure the neutral wire current in the case of balance load. And this is what it was measured, 3 milliamps. Now the neutral current is expected to be 0. So we can compare it 3 milliamps to 81.8 milliamps. And then is the neutral current much smaller than the secondary line current? So the answer is yes. Okay, so that's the balance condition. Now we go to the unbalanced condition, and for that we disconnect. And after disconnecting, we measure the neutral current again, and now it's 81 milliamps. So look, the current from the balance condition of 3 milliamps went up to the unbalanced condition of 81 milliamps. And this 81 milliamps is just equal to the phase current. So how can that be? Well, the reason is this. Look. So when we have balance and then unbalance conditions, okay? So then we have our three phasors. So the sum is equal to 0. Why the sum? Because E neutral, IA plus IB plus IC in a star connection. Now, in the unbalanced condition, we drop that current. So this is A is missing, A is missing. So now we have B and C. So then we zoom that. So here the angle is 120. So when we zoom this, we get this. We are doing here a summation like this. So now this is I neutral. Okay. So this is 60, 60. This is IB. This is IC. So then I neutral turns out to be equals to IB, turns out to be equal to IC in magnitude, not in angle, in magnitude. So neutral conducts the unbalanced current. So that's the main function of the neutral, okay? So we must not assume that always is going to be everything balanced. Okay. So then coming back to the report, measure the 4-wire neutral current again. Okay, now oscilloscope. So now we do the case for the oscilloscope. So that's in the video. So in the first part, A, channel 1 is reference. That's connected to phase A and ground on the secondary. Channel 2 is phase B. Okay, so then on the secondary. And then measure the time delay. So using the cursors, we measure 5.6 milliseconds. Determine the phase difference with this time delay. So this is the formula. What is the period here? Okay, so the period is 1 over frequency. The frequency is 60 hertz. So the phase is going to be 360 times 60 hertz times 5.6 milliseconds. And then you must write this result here. And then now, is it going to be leading or lagging? So in our case, let me see. This is what we have. Lagging. And then for the other case is move channel 2 to the third phase, C. And then we observe now that it's leading. Calculate the phases and draw a phasor diagram. So to draw a phasor diagram, this is what you should do. So A is here. Then indicate the angles. So we are going to determine A with respect to B and the other angle A with respect to C. So that's the phasor diagram. Okay. Then indicate sequence, positive sequence or negative sequence. So positive sequence means this is positive sequence, A, B, C. And then this is negative sequence. So this is positive and this is negative sequence. So as you rotate the phasors, as they rotate, because omega t with time is changing, then we get the phasor A, B, C, etc. So that's the positive sequence. Now here, as we rotate the phasors, then we are going to get A, C, B, A, etc. So that's the negative sequence. Okay. Then now you must do these calculations here. Part D. Write the 3 secondary line currents. So I put here the, we already made this measurement, 81.8 milliamps. And then we have 0 degrees for the reference. Now here you must put the angle of the second phasor, the angle of the third phasor, and then calculate the rectangular current in rectangular components. So you must calculate I neutral equals IA plus IB plus IC. So this is 81.8 angle 0 plus 81.8, angle theta B, whatever that is, 81.8, theta C, whatever that is. So this is neutral in milliamps. Okay, so then you come here to real part, I neutral, plus J imaginary part, I neutral. And that's what you write here, the rectangular components, real and imaginary, and then the magnitude IN equal square root of real IN square plus imaginary IN square. So then this current that you are determining here is going to be compared with what we had measured for the case of balance condition, which is over here, 3 milliamps. All right, so then that's the homework. Now there are a few questions here, conclusions, let's say. Well, some of these do not apply. Okay, so this omit. The square root of 3, you can answer this. So choose A and B. Then number 4, a neutral conductor in delta or in star systems. Number 5, green is for neutral or for the equipment grounding conductor. Well, okay, so this is it's voluntary, okay? Voluntary. If you want to answer this, it's fine. So then here are the so how am I going to grade this? So look, all questions must be, which are blank here, they must be filled. So that's the way I'm going to grade, right? So I will make a tally of the number of questions that need to be answered, and then depending on your responses, that's be the grade. Okay. So this is for lab. This is the last part of the meter. Okay. Now, hold on a second. Do you have questions? Okay. So then returning to chapter 11, let me see, lecture. Here. Chapter 11, what's the name of the chapter? The name of the chapter is the sign of feeders. Okay. So look at this. Look at this text here. Ampacities of three conductors in a raceway. And then the size of the conductor, which be an American wire gauge number or a KCM circular mills. And then we'll be looking at a table, conductor properties, which are copper or aluminum. Then we'll be looking at maximum allowed temperature. So let me show you that table. I put it here on the this is the table I'm talking about. Okay. So look here. The first column is the conductor size, AWG or KCM. Then the second columns, we have 1, 2, 3, 4 for copper. And then the next 4 for aluminum, the material of the conductor. Then on these headings, we have temperature. So we will have 60 degrees centigrade, 70 degrees centigrade, 90, I think it's 85 and 90 degrees centigrade. So what type of temperature is that? So that's the temperature rating of the insulation. Okay. And then the insulation types. So for 60 degrees, we have 2 types. It says TW, temperature and water, UF, underground feeder. For 75 degrees, we have rubber heat and water, THW, which is the most common, temperature, heat, and water. Not temperature. The T is thermoplastic, the heat and water. Okay. So all these acronyms are for the material of the insulation. And then that material of the insulation is rated for 90 degrees. So no more than 90 degrees on these insulations, because more temperature degrades the insulation, and eventually there'll be a failure in the insulation of the cable. Okay, and then all these numbers are called the ampacities. So what ampacities of not more than 3 single insulated conductor rated from 0 to 2000 volts in raceways in free air from the National Electric Code table. Okay. So, and then what is ampacity? Ampacity is the normal capacity. By normal, we mean standard temperature that the conductor can carry. Okay. So, for example, 150 amps for cable 1 knot at 75 degrees, the insulation. Okay. So if you require more current, if you require 230 amps, then you move downwards and then follow the increase of the cross-sectional area of the conductor. Okay. Now, all these are good for 30 degrees centigrade. Normal temperature for these are 30 degrees centigrade. Now, if the temperature is different than 30 degrees, there are going to be correction factors. So here is the line for 30 degrees. See this line here? So then on that line, we have correction factor equals unity. Now, if the conductor is cool, for example, inside of freezers or air conditioned rooms where the temperature is less than 30 centigrade, then the ampacity can increase by those correction factors. However, the opposite is true. As the temperature starts increasing, the correction factors start decreasing, and that's going to have an impact on the ampacity of the conductor. So, for example, if we have on the rooftop a conduit and it's not shaded, if that conduit is under the direct influence of the sun rays, then that conduit may get to a high temperature of maybe 55 degrees, let's say. And then you see how the ampacity of the conductor drops down to average 50%. Okay, so the temperature of ambient is very important, combined with the temperature of the insulation. Okay, so then I can show you this example. No, sorry, here. Example, okay, so here am I. This is what I want you to do now. Pay attention now, okay? So let's calculate that. And exactly so that's problem 1. 3-phase calculate numbers I secondary equals the power is 250K. The is 3-phase square root of 3. Can you look at my writing? I think so. Is that right?
Yes.
Yes. Okay, so then what else? The voltage, 0.48. Is there a power factor here? No, because it's kVA. So then what is that? That current is equal to 250 divided by the square root of 3 divided by 0.48. Is it 0.48? Yes. 300.7 amps. Okay, so then the answer is C. So that's problem 1. Now problem 2, it says correction factors. Calculate the ampacity of the feeder copper conductor. Assume T rating of the conductor. So T conductor, 90 degrees. T ambient, 36 degrees. So correction factor for 36 degrees. So that's going to be 0.91. Hold on a minute. I'll be finished in a second, right here. So T90 and 36. So this is T90, this one. And then we go down to 36. And then it says 0.91 there. Correction factor 0.91, okay? 0.91. So then the corrected ampacity was equal to 301. This is the ampacity that we determine times, times or divided by. No, I think we must not multiply. We must divide. Okay, so the ampacity, so then instead of by the correction factor like that, so then divide by 0.91, 330 amp. So therefore that is A. So finally, I know I'm over now, just one more minute. So now go to 330 on 90 degrees. So that's this conductor here, 350. So then the rating, the gauge of the conductor is going to be 350 kcm. 350 kcm. Problem 3. Gauge. Cable, 350 kcm. So that's number E. Okay. Okay, so we'll finish class now.
Sir, can
Thank you
move
for
the
your
paper up?
attendance. See you
Sir,
next
can
Monday.
Sir, can you move the paper up?
You have questions?
Can I see the last part again?
Okay. This, you mean this?
Yes, in problem 3. It's because where you were writing, I couldn't see. I
Okay,
was asking
so
if you can
table,
move the page up.
look, so when the ampacity corrected by the effect of ambient temperature, it went up from 301 amp, it went up to 330 amps, okay? So now we must look at this number in the table. So now the table, we go to column 90 degrees because that's the temperature of the insulation. And then, so this is 290, 320. So it's between 300 and 350 kcm. I'm reading now here on the first column, which is the type of conductor, the size of the conductor. So it's going to be a cable of 350 kcm. Okay, more questions? Thank you. Goodbye now.